All right, thanks for being here, everybody. We're at the MECOP Baja Dyno group. I'm Gabriel Trainer. This is Nick Bandowski, Mike Laskowski, and Eric Whitney. So what we're going to do, kind of intro, just kind of get our feet on the ground, kind of see where we're coming from. The timeline of how our project went down. We're actually a MECOP group. So we're the first MECOP group to go through UP, which means we had 2 internships our senior year. So we actually did this over a year and a half. So we'll talk about that, some design considerations and testing, and then kind of considerations we came to at the end. So yeah, this is the Baja. That's the buggy. So we haven't had the team on campus in a while, but the goal of this project was to kind of revitalize the team. So a dyno is good use for engine tuning, and to be competitive, team you need to have the dyno to fine tune it. So this kind of also aligned with our interests in hydraulics, fluids, data acquisition systems, CAD. We've got to utilize all those within this project. And this is for a MECOP group. So this is rather unique in that we had a year and a half to do this. We had a 6-month break between each semester. So this is the picture of the CVT, or continuously variable transmission. The idea of this is that it's constantly shifting to meet that ideal RPM. That's the goal. You can kind of vary when it will shift based on the internal weights and springs. You can increase the tension or add or take away weights. So the idea is, again, maintain that ideal RPM. And so a bit about dynos. This is an example of a fluid dyno, just a basic circuit. And then the idea of the dyno is to create this power curve, which can give you, we can kind of load the engine based on you can use various resistance types. You can use inertial, electrical, fluid. We don't want fluid because we have more background in fluids, and that's more of a mechanical thing. So that worked for us the best. And it just, yeah, again, some ways like an engine going, like you're going up a hill, carrying weight, it just gives you that load on a bench test as opposed to actually driving the car. So the pump we chose for ours is a positive displacement pump, or PDP. So you can see in the picture, we did a gear pump, so there's actually gears that mechanically force the water through the pipe. The advantage of this is that it has a linear relationship between pressure and load. So as we, in our case, we used a valve to add resistance on the circuit. As we turn that valve or decrease the orifice size, it will continue to pump, while other pumps, like centrifugal pumps, will actually stall and wouldn't work for our purposes. So we use PDP, and they're commonly used in hydraulic power systems.
So I'm going to talk a little bit about the timeline for our project. Like Gabe said, our project was split up over 2 semesters with a 6-month internship in between. And for this reason, one of the things we really wanted to emphasize was having a kind of theoretical and design side semester, and basically having the goal at the end of the first semester of being completely done with design, so that moving into our second semester, we can hit the ground running and start constructing the circuit. So the way that we broke this down was to begin with kind of researching dynamometers. I came from SAE Baja background. I was on the team when we did have one. And so I had a little more background on how the CVT worked in that. And so it was a little bit of a learning curve to learn how to, or get up to speed on what we were trying to accomplish with this project. And from this, we determined the intended type of dyno we wanted to use, which was in fact a fluid dynamometer, as Gabriel said. And then we went through and basically designed our system and created a CAD model of it, and created a bill of material and full construction drawings, so that when we came back in the second semester, we would be able to begin with our actual physical construction of it. Coming back this past January, our second semester, we began with inventorying our components, seeing where we were at, and as soon as we could, we dove right into the physical assembly of both the fixturing and the circuit. And then our next step was to implement our data acquisition system, which we anticipated being one of the more challenging aspects of the project. And along with doing that, we began testing the project. So one of the things that we really wanted to emphasize in this project was basically that it would be applicable to whatever SAE project came about for the school in the future. SAE sponsors the Baja team, which is kind of an off-road buggy. They also do a super mileage and a formula, which are different types of races that people can do, or students can do. And so we wanted to make it so that it was an easy system for any future teams to kind of pick up and be able to apply to their projects, specifically in order to be something that was usable for them to help improve how they do in competition. In addition, we also wanted to make sure we had adequate time for testing, as developing the correlations between pressures and powers is not necessarily a very set in stone science. It's a little bit of really kind of getting a feel for how the system runs to develop what load is going to apply to what situation. And so it's important for us to have a lot of time to test it. And along with that, having a DAC so that we could take our data and record multiple sets of data and compare them to get kind of what we were actually getting, an average of it, and be able to interpret that data. So our final design that we ended up with was, as you see here, is a fluid circuit dynamometer with a PDP, which is seen here. Due to the nature of a PDP having a fixed displacement for every revolution of the engine, you have to include a safety relief valve so that you don't blow any components. And basically what that does is this hose coming off here is if it were to get up to a dangerous pressure within the system, it would vent through that essentially and back into our reservoir. After the safety relief valve, you see our valve, which is how we apply the load. Basically, by changing the orifice diameter going through the system, it takes more power to continue to deliver the same flow rate. We initially planned for a LabVIEW data acquisition system, and at the beginning of our second semester, we transferred that over to an Arduino system based on what we had anticipated being a more straightforward process. And we wanted to use a water glycol mixture as our working fluid due to the fact that we were not sure how much temperature would be added to the system. And so therefore, we needed to have a large reservoir, and creating a very large reservoir with hydraulic fluid adds up very quickly as an expense. In addition, it was a bit of a, not a safety requirement, but being able to dispose of the water. Later on in the project, we were having difficulty with the viscosity of the water, and so we talked with a contact at Heister that our industry advisor Tim set us up with, and he recommended going to a water glycol solution, which we tried after that to try and simulate the hydraulic fluid aspects better. And our frame is just a simple angle iron fixturing. So as you see here is our CAD model of our final project. Like I said, we went through the theoretical design and calculations during our first semester and ended up with this conceptual fluid dynamometer. Our calculations that we used were kind of to estimate a maximum theoretical pressure in order to basically essentially find a factor of safety, knowing that our system would likely not reach that in order to size all of our components. We also implemented slotting mounting on any of the main components to accommodate different engines or different systems in the future, make it more customizable for other SC projects. So here again you see a drawing of our circuit, just to kind of iterate how our leading off first semester, we wanted to have everything basically ready to go into the manufacturing phase coming into second semester, so we needed to have good quality drawings that you would be able to pick up and build the system based on that. And again, another example of that. One of the things that we implemented in our project was we wanted to have a lot of hands-on aspects, and one of the things was Gabe had expressed an interest in learning to weld, and so he was actually able to take this drawing and work with Jacob to learn to weld and build the entire frame, and put a lot of vibrations into it, and has not cracked, so good quality welds. Again, here's our calculations. Our methodology for our calculations were a little bit challenging because we don't have a lot of experience with PDPs through our coursework. They're quite different in how they work than other types of pumps. And so what our kind of goal was to take the anticipated torque from the engine going through our ideal gear ratio. And what I mean by that is that if the engine were tuned perfectly and the CVT was tuned exactly how you would want it to be, at our maximum load condition, we create the highest torque gearing possible, which is a 4.5 to 1 ratio. From this, we were able to find our torques at the pump going through that gear ratio, and as a result, find our pressures that would be built in the system in that theoretical maximum scenario. And from this, we got about 3,500 PSI, which is quite high, but we were not anticipating reaching that. We were anticipating being about a third to half of that range based on losses in the system, such as the belts and CVT tuning. And here you see our pump curve, and basically kind of the major takeaway from this is to show the difference between a centrifugal pump and a PDP, which is that the relationships are in fact linear. And so from this, you can take at a set RPM, you can determine at that RPM, if you build a pressure in the system, you're going to know the flow rate, and as a result, know the power.
So like Eric said earlier, second semester was really building the actual system. So once we got all the parts and inventoried everything, we assembled the dyno, and then we started running it to test it for integrity. We ran it with analog sensors first to protect our digital sensors because we didn't know exactly what kind of pressures we were going to get. And then we proceeded to calibrate the sensors, build the circuits that we need to run the pressure sensors and for a tachometer to measure the RPMs out of the engine. So we built a circuit and developed code for that. So here, once again, is just the final design, and then here is the circuit all built up. So obviously it's right here, but we don't have the 55-gallon drum. So some of you can see it up here. I'll do it on the picture. The fluid leaves the reservoir. There's a pressure sensor before and after the PDP pump right there. Pressure sensor here. There's a relief valve that goes back to the reservoir, and then there's the needle valve over here, which we use to increase the load, and then once again the fluid goes back to the reservoir. Here is the circuit in the Arduino, or this is one of the iterations of the circuit in the Arduino that we have. The final one is up here in the front. But as you can see, there's resistors with each pressure sensor in order to make sure they're running at the optimal voltage. And then the signal is inputted to an Arduino. This was for the tachometer. This is an optocoupler. So when the spark plug basically in the engine fires, it completes the circuit on the right side, lighting up an LED, and then on the left side, there's a sensor that sees that and outputs a digital signal that there was a pulse, and then we could count those pulses in a given time and calculate an RPM. And then also up here, this is RTC, a clock basically. We weren't able to integrate it into our code, but that'll be something for future teams to integrate. So here's the code for our pressure sensor. The biggest thing is that we set the analog reference to 1.1 volts. We were getting really low pressures, and so this helped increase the resolution of our code, so we were able to see smaller change in pressures than if we had gone from the default 5 volts. Then the rest of the code is just reading the sensor, converting it to the voltage between 0 and 1.1, and then we printed it to a file which we exported to Excel, and we could calculate pressures from that Excel sheet. And then this is the tachometer code. It's a simple counter. When one of those pulses fire from the optocoupler, it just counts a 1, and then we average that out over the time that we ran the engine. Obviously, the RTC will, in the future, if teams improve on this code with more Arduino experience, they can have more real-time RPM values.
Yeah, so I'm going to talk about experimental results. We were able to get a proof of concept, so we saw a rise in pressure as we tightened that valve, which translated into a graph which I'll show you shortly. Our pressures, though, were significantly lower than what we were expecting. As Eric kind of touched on, there's inherent losses in the system, but we had already accounted for that in our calculations. And kind of the sense that we got from some iterative exploration of different potential problems, we kind of honed in. We're pretty certain that the water is kind of the limiting factor as the working fluid. So we weren't, although we were able to put a load on the engine, it wasn't great enough for it to downshift, which is what, again, Eric was talking about with the ideal ratio of 4.5 to 1. So that results in a lower pressure but a higher flow rate than expected. So we were seeing about 10 gallons per minute as opposed to what the calculations said before was what we were looking for. So this is one of our pieces of data. So you see on the x-axis is time, y is pressure, y-axis is so the blue kind of curve is the outlet pressure, which you can kind of see is passive. And then the inlet pressure is before that, before the pump. So the strange thing about this, though, is because we, as you saw in the CAD model in the picture, it's an open reservoir system, so we were expecting the inlet pressure to remain about the same, if not significantly lower than this, because it is open to the atmosphere. And so that's something that we tried to investigate. Unfortunately, could not uncover the reason, but just something to know. So some of the challenges, we had a blown engine, and this wasn't a fatigue analysis project, so that wasn't really our goal. We had what we believe happened was that a connecting rod came loose, or was rattling around, something kind of ejected from the crane casing. So kind of what we did to remedy that was we had to kind of splice two previous engines together from previous iterations of the Baja project. Thankfully, Shiley has a plethora of stuff in the basement that we had access to. Baja stuff was there, so there we go. So the Arduino its sensor interface required additional circuitry, so kind of we had a simplistic goal of what we thought we needed the Arduino to do, which is simply read the voltage from the pressure sensors. But we thought this because we also thought we would have access to the Baja team's proprietary DAXIS or tachometer system. We tried using the sensor that's attached to that system, and it would not work. It's a Hall effect sensor, so essentially you're moving magnets around and seeing how the magnetic flux changes as a result, and a change in current in the wire. That didn't work, so we had to kind of try implementing the optocoupler to count iterations. And so you can kind of see here it's a little messy, but right, it was iterative attempts and a lot of support from Jared, which I'll do things later, but he did a lot for that. And then yeah, so we had a delay in the shipment of parts, so it's about back about a month and a half. And we also had some small changes on our bill of materials, which kind of affected some of the, not crucial components, but definitely important parts of our system. And again, back to the timeline, it really is hard to do half of your project, set it down, and then come back up and expect to be back up to speed. So there was a little kind of a refresh time that we had to invest and kind of remember what we were working on, some of the theory and stuff like that. So some further improvements, obviously, the kind of main one is the water that as I said before, we think that was our limiting factor, so changing into a material or mineral oil would be preferable. And then kind of improve the Arduino code, so perhaps team members on the next iteration of this, if that is a possibility, would have a little more experience in Arduino coding and perhaps circuitry. And so one of the things we encountered with this kind of iterative process to make the circuit board was a little bit of fraying of the wires, which wasn't a huge inconvenience, but certainly something that would be eliminated with the permanent circuit. And further investigation of the weight sets and springs. So the whole idea was to show that we could get a load to tune the CVT, and unfortunately we couldn't quite tune the CVT as we wanted to because the load was significantly less. So that's something that we would encourage future groups to work on. So thank yous. Dr. Lule was our faculty advisor. Tim Scheinman is here. All right, cool, sorry. And he introduced us to Ken McCurdy, who's a hydraulic specialist, which was very helpful in just kind of helping us troubleshoot through some of the issues. I mean, as we said, we tried water initially, we tried the water glycol mix, and that still did not yield higher pressures, so we attempted that. And then just everyone else was great in kind of expanding our core skill set because we are all mechanical engineers, so some of the circuitry and stuff like that was beyond us. So everyone was just great in kind of giving us an extended network of resources and knowledge. So we're very appreciative of that. So thank you. Some resources, and then any questions?
Your pressure curves, you had the horizontal axis as time, but what was the scale? And what are we looking at, seconds or milliseconds?
So it's in seconds. The main thing is this part is where we're tightening down the valve at a constant rate, but obviously we couldn't do that perfectly constant. Here's where it's fully closed, and then when we open it back up. So we just wanted to show that as you tighten down that valve, the pressure's increasing, and then we hit a maximum until we open it up.
How's the next group going to know how to use this thing?
We're planning on putting all of the Arduino codes on a flash drive to probably leave with the system or leave with a future Baja team. I know some doing it for their senior design next year. The code is fairly simple to just run as it is now. We'll obviously put, we'll probably comment the actual code a little more, or just put in a Word document with just steps. But as it is now, you just download Arduino, which is free open source software, and then just send it, and it just reads right away. So.
I was going to say, as far as the actual system goes, our actual report on this project is fairly in-depth as far as our design considerations and the calculations that we used. It gets kind of dicey trying to explain that all in a presentation, but we do go into the details on that. And so there will be a copy of that left with the project as well.
Since you're the first MECOP students, man, I kind of would like to get a sense, would you have been more comfortable with 2 one-semester projects, or do like this, do a semester, take time off, and then really come back? Do you have your thoughts on this?
I don't know if I can speak for the rest of us, but I think personally, I think 2 smaller projects might be more manageable. I mean, we encountered, it's cliche, but we encountered a lot more problems than we thought we would. That's kind of across the board, everyone's experienced that. But because of that, I would almost say just this, sometimes the scope can kind of explode more than you would like. So potentially 2 smaller projects might be more manageable.
I like the design and then the build. I think it worked well. I just think it's just, we're the first group, we're the guinea pigs. We got to figure out for future, how to make that work. And it's just a lot of more planning on what to do when we come back. So I think it can work. It just needs to be improved and that'll happen. But I like having the large scope, and being able to design the build. I like that. It was good. And people have the industry knowledge, get that knowledge, and then come back and utilize that. That's helpful.
I think that actually is something that we talked about in our first semester while we were kind of figuring out how senior projects were going to work at all. Was that this project was something that had a kind of hands-off in the shop aspect of it, doing a purely design phase, and then the second semester was more of a hands-on building it and then testing. So in essence, it almost was sort of like 2 small projects the way that we broke it down. So in certain projects, I think it can work well. It just has to be something that you identify early on how you're going to break it apart.
Yeah, I like